Hi everybody. So I thought I'd make this video because I was getting a lot of questions about the crash the cars thing, and I'm going to show you one way to do this. This is the way that makes sense to me, and it's probably going to be more helpful to you to your group exam. But there are actually many ways to solve this problem that I've seen. But yeah, so I've got the situation here. Here's how the problem is set up. The problem is set up so that you've got two cars that are set 200 centimeters away from each other. So the blue car, I got at the 0 mark here, and then the red car, I got at the 200 centimeter mark here. So that's kind of the first situation right there, and they're both moving toward each other. I made up these velocities, so please don't think that these are the actual velocities of the cars. Okay, and you can make a prediction. You often want to just like make a prediction of where you think they're going to land. So if this car is moving faster than this car, would you think that they're going to meet directly in the center? No, probably not, right? If the blue car is moving faster than the red car, you probably think they're going to meet somewhere maybe over here. So that's what I'm going to say is my prediction. I'm going to say, maybe there. Now that's my guess. And now I'm going to calculate where exactly they're going to meet. Okay. So I can then, you want to establish an origin. An often good place to put an origin is at the 0 mark here. So that's my origin right there. So that's where I'm going to make measurements from. So, and I'll have the blue car, I'll have an initial, is right here. So the initial position, I'm going to say the, yeah, I'll say the initial position of the blue car is right there at that dot. And then the position of the red car, is all the way, because again, position's always measured from where the origin is. So the position of the red car is all the way over here. So this is the initial position of the red car, I'm going to say. So the initial position of the red car, which is 200 centimeters. That's how far away it is. All right. And then this is what I would consider my initial moment. So here's my initial moment, is this right here. And then I'm also going to want to establish what's my final moment. Oops. So that was my initial moment. And then this will be my final moment. Give it a bit of a space. So here's my final moment. And at my final moment, right, both of the cars are going to crash. Let's see. So for simplicity's sake, I'm going to get rid of the arrows. At the final moment where I'm saying this problem is going to end is when both cars hit each other, where I think they're going to meet. So this would be, and I'll call this, I'll call this my final position. This is the final position. So this is the final position of the blue car, and it's the final position of the red car. So that's the final position of both the blue car and the red car with respect to my origin, which I made back here, right? Initially, they were in separate positions. The blue car was here, the red car was here. And then once they crashed, this is where my final moment is. Now their final position is the same. And I'm just going to call it X as opposed to calling it XB and XR because they're the same final position. Okay, now let's use let's use an equation. What I'm going to recommend is basically using the equation that we had, that the velocity is the displacement divided by the time. That's the definition of the average velocity. And hopefully you got both cars, the velocity of both cars. I'm just saying that it's 1 centimeter per second for the red car, 4 centimeters per second for the blue car. Okay. So multiplying both sides by t, and you'll get that the displacement is equal to the velocity times the time. So for something moving with constant velocity, this equation works. Often we call it divot. But it's important to remember divot, and for this problem it's important to remember, divot is actually the final position minus the initial position equals the velocity times the time. And we're going to make a divot for both the blue car and the red car. So we're going to do the same thing for the red car here. It's going to be the displacement here. Let's make all this blue just to make it a little more easier to see the difference. So the displacement is equal to the velocity times the time. And then this will be all for the red car. So the final position of the red car, because again, the displacement is the final position minus the initial position. So it's the final position of the red car minus the initial position of the red car equals the velocity of the red car multiplied by the time. And then this will be the final position of the blue car, initial position of the blue car, the velocity of the blue car multiplied by the time. And so these are all our variables, xb, x naught b, vb, and t. And here is all the stuff for our red car. Final position, initial position of the, oh, sorry, that's the red car. Velocity of the red car, and the time. All right, and so I can start filling in things that I know. Let's see. I know the initial position of the blue car. At the initial position, when time starts, so this is at when the time is 0, starting at time equals 0, that the initial position of the car is at 0. And then the initial position of the red car, right, with respect to my origin is all the way over here. So the red car is at the 200 centimeter mark. All right. So I'll make that 200 centimeters, right? 200 centimeters to the right. Let's see. What else do I know? Oh, I know the velocities. The blue car is moving to the right at 4 centimeters per second. So I'll write down the velocity of the blue car is 4 centimeters per second. I'm using centimeters because the numbers are a little easier. Whatever you use, centimeters or meters though, just make sure you're being consistent. All right, and then I also know the velocity of the red car. Velocity of the red car is 1 centimeter per second. However, it's 1 centimeter per second to the left. So I want to make sure I'm being consistent with the definition of a velocity. That's going to be negative 1 centimeter per second because it's pointing to the left. So if I wanted to now fill in these equations, let's make this a slightly different color so that we're not. So the equation for the blue car is going to be the final position of the blue car, which I don't know, that's what I'm looking for. You know, what's the final position of the blue car, minus the initial position of the blue car, which is 0, equals 4 times the time, which I don't know. So this simplifies to the final position of the blue car is equal to 4 times the time. And then for the red car, we got the final position. So using that equation again, it's the final position of the red car minus the initial position, which is 200 centimeters. That's the initial position of the red car, equals the velocity of the red car, which is negative 1 centimeters per second times the time. So again, I'm going to isolate the final position of the red car, and I'm going to get, and I'm going to add 200 to the right. So it's going to be 200 minus the time. So now I got these two equations, and I want to figure out a way, how do I relate these two equations, right? Because if you got two unknowns, you can solve with two equations. So yeah, okay, let's see if I can do that. Because this is, again, what we call a simultaneity problem. And simultaneity means you're in the same point at the same time. And the same point, that's basically meaning you're in the same position at the same time. So, and this is what we're doing. When time starts at t equals 0, they're 200 centimeters away and moving at different speeds. But then whatever this time is, when they actually crash, they're at the same position. They're at the same position. So when they actually crash, they're at the same position. So that's what I mean. They're at the same position at the same time. So the time that they meet is going to be the same. So if I started if I started a stopwatch here and here, right, at the same moment, when they crash, they're going to crash at the same time. So they're at the same position at the same time. So in other words, again, if I know that the final position of B is equal to the final position of R, that's going to be I'm just going to call it the final position X, just to make things easier on myself. So this is going to, from that idea, is going to change into final position is equal to 4t, because this is where they're going to meet. And then for the red car, it's going to be the final position equals 200 minus t. And if, here, let's rearrange this. So it's going to be 4t equals x. And now, if both of these are equal to x, I can set these equations equal to each other. And so I'm going to get 4t equals 200 minus t. And now I'm going to solve for the time. So I'm going to add t to both sides. It's going to be 5t equals 200. And then you got t equals 200 divided by 5. Oh, I don't want to screw this up. What was that? 40? 40? That's what I think. Yep, 40. So the time is in 40 seconds they're going to meet each other. It's quite a long time. Okay, now again, your numbers are going to be different because you're going to use actual values. I just made mine up. So now that I got that time, I want to find out where they're going to meet, where they're going to be. And I'm going to show you I can plug the time into here or into here. Because what these equations are doing is they're telling me the final position of the blue car given the time. So basically what this equation is telling me is, you give me the time, I'll tell you what the position of the blue car is. This one's saying, you give me the time, I'll tell you the position of the red car. And I can plug the time into either of them and I'm going to get the same position. Why? Because they're at the same position at the same time. So using this equation here, I'll take it, copy. Let's throw it over here. Paste. And so plugging in the time, which is 40 seconds. So the final position is going to be 4 times 40, which is, so the final position of the blue car is 160 centimeters, 1600. That'd be scary. So 160 centimeters. All right. So there we go. And then I'm going to do the same thing now for the red car. Copy. Let's do it over here. Paste. So again, plugging things in. The final position of the red car is equal to 200 minus the time is 40 seconds. That's when they meet. So the red car is going to be also 160 centimeters. So it didn't matter which one I plugged in. They're both going to be the same. Why? Because physics works. And then just to double check, so my units are in centimeters, so that's good, right? My units are in centimeters. And then I can also look, 160, is that where I predicted it would be? Ah, yeah, 160 centimeters makes sense, right? If this is 200 centimeters, halfway in between will be 100 centimeters. So that means here, where it's 160 centimeters, it's definitely in between 100 and 200 centimeters, which is where I predicted it'd be. So odds are that's going to be my prediction, 160 centimeters. Again, that's not what you're going to see in the video, or this is not going to be your guys' solutions necessarily, because I just made my numbers up. But hopefully that helped, and all right, see you guys. Bye.